Hi, my name is Joshua Thompson, and I'll be discussing nuclear waste and storage, specifically at the Hanford site. So an overview is I will discuss radioactive decay and its various properties. Then I'll discuss nuclear power production, specifically surface storage and versus deep storage of the nuclear waste. And then we'll go into how the Hanford waste storage was conducted via the tank farms and then current waste storage via vitrification. So radioactive decay is basically energy emission in the form of ionizing radiation. So there are three different types of radioactive decay. The first is alpha particles, which is a helium-4 nucleus, which that's 2 protons and 2 neutrons. And then we have beta particles, which is either an electron, which is beta minus, or a positron, which is beta plus. And then we have gamma rays, which is just pure electromagnetic radiation. The elements in the periodic table can take on different forms. Most of them are stable, but if they become unstable, the radioactive decay is their attempt to become stabilized. If you look at the figure on the right, you can see that alpha particles can be stopped by a piece of paper. Beta particles require thin plates made of wood or aluminum, and gamma rays in orange can be stopped by lead, iron, or other thick metal plates. And so an example of radioactive decay is radiocarbon, which is found in the atmosphere. And if you look on the example on the bottom, radioactive carbon, or C14, decays into nitrogen 14 plus an electron plus an antineutrino. And so when it decays, when a radioactive element decays, a radionuclide transforms into a different atom. And normally this is only done one time, such as in the case as radiocarbon, and it decays into nitrogen 14. However, uranium-238 creates what is called a decay chain, which you can see on the figure here, where through different processes it decays into various types of radioactive elements, eventually getting to a stable element, which is lead-206. So surface versus deep storage. So first, the near-surface disposal facilities are at the ground level. If you look at the figure on the right, you can see these spent fuel pools, which contains the radioactive material. Now, these facilities are on or sometimes below the surface where the protective covering is of the order of a few meters thick. Waste containers are placed in constructed vaults, and then when the vaults are full, they are backfilled. So eventually they will become covered and capped with an impermeable membrane as well as a layer of topsoil. And these pools are made of reinforced concrete with steel liners. And the water inside is typically serving both to shield the radiation and cool the rods. As the pool's near capacity, utilities move some of the older spent fuel into dry cask storage. Now, for deep storage, the long timescales over which some waste remains radioactive, it has led to this idea that if we can dispose of these nuclear waste in underground repositories, then it'll be farther away from any environmental or human effect. And so they're isolated through engineering as well as natural barriers that are made of rock, salt, and clay and other various metals. So deep groundwater is generally devoid of oxygen, and so this minimizes the possibility of chemical mobilization of the waste. In the image on the right, you can see an example of deep storage. You see hundreds of these nuclear waste barrels. And so, one example of deep storage is the mine repository, comprising tunnels or caverns where the package waste would be placed, as you can see here. And a lot of times, they'll try to use the native elements found in the caverns, such as copper in one example, and this allows for the copper to protect from the radioactive materials leaking out into the surrounding environment. So the Hanford site and the waste storage there. So after irradiated fuel rods were taken from the nuclear reactors, they needed to be processed chemically in order to extract the plutonium that was created inside of them. And so they were exposed to a series of chemical processes, and this would dissolve away the fuel rod and leave just the plutonium itself. Now, these chemicals became a waste byproduct of producing the plutonium and had to be disposed of. In addition to that, since they were containing a radioactive material, they were themselves radioactive. So early on, Hanford scientists understood that these chemicals and radioactive waste could be hazardous to people and the environment. So they built storage tanks that were about 55,000 gallons to more than 1 million gallons to hold waste. And they put these tanks in the subsurface, the near subsurface of the earth. And the early tanks were constructed out of a carbon steel shell surrounded by reinforced concrete, and this later became very important because of how much radioactive waste can exit anything less than concrete and steel. And the carbon waste generated, though, were more than the capacity of the tanks. So some of the liquid waste ended up being put into holding facilities, and some was directly poured into open trenches because they could not contain it inside of these tanks. And so some of the waste that were put into the tanks actually didn't stay there, as they didn't account for the fact that if something is radioactive, remember, heat is quickly moving particles, and when you have radioactive decay, it builds up pressure and heat. And so an estimated 67 of these tanks leak some of their contents into the ground. And so some of this liquid waste migrated through the ground and has reached the groundwater itself. And so crews continue to search for new novel technologies which can facilitate the removal of the semi-solids and solids out of these storage tanks. So the tanks weren't designed to go back into them, and so a lot of the opening valves are a foot in diameter or less. And so they've had to create inventive and creative ways of infiltrating the tanks and retrieving these semi-solid and solid wastes. And so now, with the extraction of this waste, what they have begun doing is processing the waste at what is known as a vitrification plant. And so vitrification is the process of mixing the waste from the underground storage tanks with glass-forming materials at very high heats. And this liquid glass is poured into stainless steel canisters to cool. And so it allows a better containment of the radioactive material than simply putting them into storage tanks. And so once this is cool, the now solid vitrified waste within the canisters can be disposed of permanently and safely. And approximately 56 million gallons of radioactive and chemical waste are waiting to be vitrified. And so the conclusion, so if we think about the pros and cons of deep storage versus shallow surface storage, you really can't say one is better than the other. And this is because shallow surface storage is predominantly for these short-lived radionuclides. And so the deep storage is to store the radioactive waste that will become stable thousands of years from now or 100 years from now. And so we want to put away the long lived waste inside these deep storage. So as long as the storage management is conducted properly, where you have short-lived radioisotopes being stored on the shallow surface, and then these long-lived radioisotopes being stored in the deep storage, they're both good means of storing radioactive waste. And so the consequences of the Hanford storage tanks is that the pressure buildup created heat, and over 67 of the storage tanks leaked into the surrounding soils, which then contaminated the groundwater. And because of poor management, sometimes they just dump the waste right into open trenches. And this leads to an awareness that there needs to be a proactive kind of drive for any nuclear plant. You have to look at the environment and see what is around you and what could harm your nuclear plant, and think about what will happen 100 years from now or 200 years from now in the area that you're creating this nuclear energy.